Irina.
Thank you for introduction. Good morning, everyone. Thank you for coming for the early talk. For those who don't know me, I'm Irina Zhuravleva, and I'm assistant professor from University of Chicago. So in this session, we're switching to very large scales, to scales of clusters of galaxies. And I will basically talk about gas motion / turbulence, which I'm not going to distinguish in my talk, in this hot volume-filling gas that constitutes the intracluster medium, right? And I will just very briefly highlight some observational results, what are the challenges, and if there is any time, talk about some potential future perspectives. And I will be mainly highlighting works from my group members in Chicago that we also did together with our collaborators. You can see their names on the slide. So let's start from beginning. What is the best velocity map we have at this stage? Well, still from Hitomi satellite. We launched back in 2016, and the satellite looked at the core of the Perseus cluster, the inner few tens kiloparsecs in radius, and it provided high-resolution spectra where we could resolve individual lines and measure line broadening and shift, right? Basically, we got two maps of velocity dispersion and variations of a bulk velocity, and you can look at typical numbers. So velocity dispersion, 100, 200 kilometers per second, and variations of line centroid are also about plus minus 100 kilometers per second. So is it a lot? Let's use these numbers and convert them into Mach numbers, right? So we are getting numbers of 0.3, 0.45. So we're in a very subsonic regime of motions, and this is not surprising. We knew that from indirect methods, and it's broadly consistent with predictions from simulations. In terms of contribution of turbulent pressure to the thermal pressure, we get the ratio from 5 to 10% roughly. All right. Comparing these two maps, we can also try to put some constraints on ejection scales. Given the data, we couldn't have very tight constraint, but we found that it should be below 100, 200 kiloparsecs or so. So that's the best map we have at the moment. Unfortunately, the life of the satellite was quite short, only about a month, and it was clear the data was so rich we had to launch a new satellite, and we did it about 5 months ago. We launched X-ray imaging and spectroscopy mission, or XRISM for short. That's a picture from the Tanegashima Space Center where it was launched. So this is a collaborative project between JAXA, NASA with ESA participation. Covering today is RESOLVE, which is high-resolution X-ray spectrometer, X-ray microcalorimeter. So it took us some time to cool it down, and we reached the required temperature, about 50 microkelvin of the satellite, and we checked that in flight, spectral resolution was less than 5 electron volts. The requirement was 7, all right? So we are doing really great, and this resolution is a factor of 20, 30 improvement compared to other, the CCD type of detectors that we have right now. So that looks great. However, there is one issue, and one issue is that there is an aperture door that is covering our detector, and we were not able to open it, even though we tried 3 times at this stage. And what it means in practice, it means that our soft X-rays are currently blocked, right? So if effective area that we were initially supposed to have is black one, the one that we have right now is a blue one. What does it mean in terms of, our astrophysical observations? It means that if you want to do some soft science, like if you want to look at X-ray emission from small halos like galaxies, for example, you may not be able to detect anything because they are mainly emitting in the iron L, so below 1 keV. But if you're talking about cluster science, and in particular the topic of this conference, turbulence in clusters, we don't need to worry too much because we are basically dominated by lines at 6.7 keV, and we still have a pretty good response of the instrument there. We just need to probably adjust our exposure. All right, so that's the current status. Investigation ongoing. We have pretty good idea what is happening, and there will be other attempts in the coming year to open it. Anyway, the decision was made to move forward and start observations. And I just want to show you the spectrum. The first release that we released in January this year, this is a spectrum from the supernova remnant N132D, extended X-ray source. This is how it looks. And this is a spectrum that we've got, all right? It looks amazing, right? So we see soft lines of silicon and sulfur, and of course, if we go to high energies, we start seeing iron. And this looks fantastic. The spectrum that we have right now is shown with a gray curve over here. So I don't need to comment that we are resolving finally lines. That looks exciting. So another chunk of data, last week, we actually released a chunk of the data for the community. We uploaded it for everyone to play with the data and hopefully write the best possible proposals, right? The deadline for proposals is April 4th. So the data is basically coming from the core of the Perseus cluster. Region is very similar to the one that Hitomi observed, not identical, but very similar. And this is just the raw data I'm plotting here, not even doing anything, right? It's a broad band from 1.5 keV all the way to 10 keV. And again, we see, of course, continuum and a lot of emission lines. And these purple panels just show zoomed in region. This is a soft part of the spectrum where we see sulfur lines mainly. Helium-like triplet is the strongest lines. We can resolve resonance, forbidden, and intercombination lines very easily. And of course, a higher energy part of the spectrum where we see nickel lines and hydrogen like iron. So a lot of rich information. We just started working on it, right? So the science team just getting the data, and we officially started our performance verification phase a couple of weeks ago. So we have a very intensive program for the next 6 months. So stay tuned. There will be a lot of results coming. And of course, I'm sure there will be even more exciting science coming from the general observer program. And this is just a website where you can download the data. All right, so that's a quick update on CRISM. That's all I'm going to show today. So in the rest of the talk, I will focus on indirect methods of measuring gas velocities in clusters of galaxies. And I fully agree with Susan, who mentioned yesterday that we have a lot of rich data. We just need to come up with a very clever methods of extracting information from there. I want to focus on this method of measuring gas velocities from X-ray surface brightness fluctuations and give you some updates. So the idea is not new, and I'm sure many people in this room already heard my talks many times, but for those who have not, a quick reminder. Back in 2014, together with my collaborators, we came measuring velocities just using imaging, X-ray imaging data of clusters of galaxies, which have a lot, right? We collected a lot of beautiful deep images in the last 25 years or so. So what is the idea? So we know that clusters are stratified systems where we have gradient of density and entropy, and motions are mainly subsonic. That's what is our realistic expectation. So if clusters are in ideal hydrostatic equilibrium, they will appear as, spherical systems, right? And if there are any perturbations produced by motions, they will be immediately imprinted in the images, right? So similar idea, if you go to the ocean, you look at the size of the waves and you can clearly see what is the velocity, right? The higher the wave, the larger the velocity. So if we go through some analytical arguments, we come up with a simple statistical relation between the amplitude of density fluctuations that are imprinted on X-ray images, and we can extract them from the images to the basically Mach number. The only issue here is the proportionality coefficient, right? Which from analytical argument is just a square root of the ratio of pressure to entropy scale heights, and it should be of the order of 1. But of course, there are a lot of assumptions. So ideally, we need to verify this coefficient with observations and simulations. So observations are still coming with CRISM. Definitely, this is one of the things we're going to do. But we can now use simulations, and just wanted to highlight very briefly a recent work done together with graduate student Mendy Chen, where we basically analyzed a very large sample of clusters of galaxies from cosmological simulations, measured delta rho over rho, measured velocities, the function of wave number, and try to calibrate this proportionality coefficient. And what we found that in relaxed clusters, this is about 1 with a scatter about 10%. And of course, it gets, it's also about 1, but the scatter is larger in unrelaxed systems. But still, the scatter is about 30%, all right? So seem to be working pretty well. Now let's apply it to reality. And here I wanted to highlight a work of another graduate student, Annie Heinrich, who basically analyzed all clusters that Chandra has observed with deep enough exposure, which is maybe 50, 100 kiloseconds, where we can do this measurement, right? And there are in total 80 clusters relatively nearby. So here you see redshift, the mass distribution. And we analyzed all the regions within R2500. Why R2500? Well, these are the regions where we realistically can get data. We don't need to worry about background, all right? And to simplify our interpretation, whenever applicable, we were also excluding central cool core regions where cooling is very short. The cooling may affect our interpretation. Very often there is also agent feedback. So to avoid this complexity, we remove cool cores and look at everything basically outside cool cores all the way to R2500. And the top figures here show our results. Delta rho over rho is a function of wave number or scale on top, and individual curves corresponds to individual clusters. Color shows the uncertainties due to Poisson noise, and the background gray region shows sample averaged values, right? So you can see the scales we are probing. They are roughly, well, in these units, it will be about, on this side, it will be 500, 400 kiloparsecs, and we can go all the way to like 80 kiloparsecs or so. So this is the best we can do with the current data. All right. So clearly perturbations are smaller, typically 10–15% in relaxed systems, and they are probably a factor of 2 higher in under-relaxed systems. And I'm not talking about all the possible systematics here, just want to warn that, sorry, you have a question? Yes. We assume when we are doing reconstruction from 2D to 3D, we assume that there are a lot of fluctuations along the line of sight and that their phases are uncorrelated. Yes. Sure, yes, isotropic, yes. And that was tested also with simulation, at least in the context of relaxed clusters. That seems to be working pretty well, again, coming from simulations when we applied the same process. So that's what we've got. Now, before we switch to velocities, I wanted to show you an interesting comparison with numerical simulations, right? So now we have this new exciting observable for many systems. We can actually see if they're consistent or not, right? And this figure shows with blue color our observational results, sample averaged, and the red ones show prediction from simulations. And again, we are looking at relaxed, interrelaxed clusters and all together. Right, so the good news is that when we look at intermediate, unrelaxed, so all systems together, we see that there is a pretty good consistency with simulations. However, if you look at the most relaxed systems, we see that they are consistent on large scales, on scales of a few hundred kiloparsecs. However, as we go towards smaller and smaller scales, we see that there is clear difference. And at scales of 100 kiloparsecs, we see that fluctuations in observations have basically are a factor of 2 at least larger than what is predicted in simulations. And given that these relaxed systems are often used to, test scaling relations for cosmology, we thought that this is really worrisome and we need to investigate this further. The first, of course, idea, we thought that maybe it's just resolution of simulations. We don't think this is the case. We do see resolution effects at much smaller scales, which we're not even plotting here. And we still think that 100 kiloparsecs is something we can reliably resolve within this regions in cosmological simulations. So our current hypothesis is that it's directly related to the implemented baryonic physics in simulations. And if you're a person who is doing these simulations, please pay attention to this observable, because in principle, it could actually test how you implement your, this interesting physics of feedback and cooling in your simulations, all right? So that's just delta rho over rho. Now, let's use the simulations and convert it into velocity using our scaling relations with updated correlation coefficients. Velocities are shown in the bottom. This is one component versus wave number. Again, individual clusters, and the gray region shows averaged over sample. Admittedly, within the uncertainties, we are basically consistent with any physically motivated model of turbulence, including, of course, Kolmogorov one. That's the best we have right now. And we are basically resolving maybe maximum like 1 order of magnitude and k, even less. So now we can actually integrate it over scales and look at the global characteristics, in particular, look at the Mach number of velocities or the contribution of non-thermal pressure to the total pressure. And these are all the systems that we looked at, and the red points basically show results if we just integrate within K-min and K-max that we can, observe in each system individually. And the blue points show what if we find the best fit in power law to the observed spectrum and integrate it from R2500 all the way to 0 kiloparsecs, right? So K-min, K-max is kind of our uncertainty here. So the blue points could be considered as an upper limit, right? So what we find that the Mach number, one-dimensional in relaxed system could be as low as 0.05, and in emergent system it could be all the way to 0.6, 0.7. So these are the numbers we are having. All right, so this is velocity power spectra. We get it with many systems. Of course, we'll test it, we'll calibrate it further with CRISM and see if our systematics are indeed strong here. But that's what we have right now. What can we say about gas microphysics if you have this measurement? All right, so I'm switching gears a little bit in my talk. In particular, I wanted to discuss gas viscosity in the bulk ICM, because there is a big question what the Reynolds number in the ICM. If it is just Coulomb, hydrodynamics with Coulomb collisions, Reynolds number would be very, very small, and we don't even need to talk about turbulence. But we know that there are magnetic fields, even though they're not very strong, they may modify the behavior of particles on small scales and increase collisionality of particles, and things could be very different. So can we test this? Well, according to plasma physicists, we have kind of a simple prediction. That's my view of all the complexity. So we know how the energy spectrum of turbulence would look like if we just have, hydrodynamics with Coulomb collisions. It will follow Kolmogorov spectrum, and we would expect that on scales comparable to the Coulomb in free path, we will have basically exponential cutoff, right? There will be no motions at all. And plasma physicists are telling us that because of magnetic fields, there could be, there could be electromagnetic fluctuations that will be basically scattering of particles, increasing their collisionality, and in this case, we may expect continuation of the spectrum all the way to the ion gyroradius, basically, right? So this regime over here seems very interesting, and we were trying with observations to test it and see whether we can actually rule out one of the scenarios, all right? Now that we can measure velocity power spectra. The challenge here is that the mean free path usually is quite small in the brightest classes of galaxies. Accessing it through simulations is quite challenging. Nevertheless, we proposed a very deep observation of a coma cluster of the center, where the mean free path was already realistic 10, 20, 30 kiloparsecs. However, we still need a very, very long observations, about 2 weeks, just looking at this region. It's not very interesting from astrophysical point of view, but good for us, for plasma experiment. And we basically measured density fluctuations over here, also in the center, and so like which model we are mainly consistent with. So skipping some intermediate steps, showing directly results. So this is amplitude of density fluctuations versus wave number in some convenient rescaled units, so we can plot all things consistently in one figure together. Measurements in the central region in red, in the offset in blue, and this vertical region just show the mean free path in both systems. So what we found that this offset region is actually approaching the mean free path, and we don't see any exponential cutoff. In fact, we are way more consistent with the Kolmogorov slope rather than exponential cutoff, and it immediately rules out the simplest scenario where we have hydrodynamics with Coulomb collisions, and indeed we do see that basically magnetic fields are modifying small-scale interactions of particles. Now we can be a bit more precise and try to compare these predictions, these observations with predictions from direct numerical simulations of Hydra turbulence, and they are plotted with black curves over here. The solid one corresponds to the velocity, and the dashed one are the power spectrum of a passive scalar, which is density in our field. And we know that the spectrum shape depends also on conduction, which we, in our case, parameterize through the thermal Prandtl number. And Prandtl number 1 is the maximum we expect in ICM, and very likely it's lower, and the lower is the Prandtl number, the earlier is the cutoff, all right? So the takeaway message here is that we have huge disagreement between observations and direct numerical simulations of Hydra turbulence, which again reinforces our main conclusion that we can comfortably rule out the Kolmogorov model, all right? So now it's kind of interesting also to using these simulations and observations to find kind of at what parameters and what particular viscosity we'll have rough consistency between DNS simulations and observations. And we know that if we try to suppress Spitz level of viscosity, these theoretical predictions will be moving closer to observations, right? And at some point they will be consistent, and here where we stop and we say, well, this is a constraint on our viscosity. Right, and we do it for different Prandtl numbers, and again, skipping intermediate steps. Just you can look at the summary figure where we show suppressed Spitz viscosity, 3 minutes, wow, versus Prandtl number, and the dashed region shows basically a parameter space where we're consistent between DNS simulations and observations, all right? And this is just pure Hydra case. So the conclusion is that regardless of the level of thermal conduction, which we admittedly do not know, the Spitz viscosity is suppressed at least by a factor of 10 in the Coma cluster, all right? Now that we have a sample of clusters, we can actually test it for selected systems from the ANIS sample. The data was good enough, so we can actually resolve a pretty broad range of scales. And the takeaway message here that we see kind of consistent results. So it's not just a Coma cluster. Suppressed effective viscosity seem to be generic property of the ICM. All right, I have maybe just a couple of minutes left, so I will skip part on turbulent accelerations. Anybody's interested, I'm happy to talk to. And we'll just very quickly say a few words about the possible future. 1 minute left. Well, I'll do my 2 minutes. Great. Thank you. So far we are focusing on relatively brightest inner regions within clusters, and this is great. Crescent will be observed them too, but there is way more interesting stuff we can do in cluster outskirts and filaments and regions where both are interacting with each other, and also within the CGM, right? So these hot halos universe around galaxies. The challenge is that these regions have very low density, and we need a very new type of mission to do that. The mission that basically has very large field of view, large effective areas, so that they can collect photons very efficiently, and it should also have very, very high spectral resolution, even better than what CRISM have, to basically decompose signals from the Milky Way foreground and the source itself. So I'm not going to talk about line emission map, but this is one of the missions we were working and proposing as, response to the NASA call for the probe missions. So basically designed to study very faint extended X-ray sources. These are formal characteristics of the instrument. Again, my talk is not about that, but if we have this type of mission, the second question we have, what actual information we can extract from our outskirt regions? We should keep in mind that these are very complicated multi-phase and multi-velocity regions, right? And this is like one of the things that with my postdoc in my group was Sanyao Zhang was leading. Basically, we did all this end-to-end post-processing of simulated clusters where we know what's in there, we generate mock stuff, we generate mock X-ray image, and then we apply X-ray tools and see what actually we can recover, right? And here I just highlighting a couple of figures. So the top figure shows the phase space. This is velocity versus three-dimensional radius, and temperature is in the color. So you see how complicated are intracluster mediums. Within the inner regions, we are dominated by one hot temperature component. But as we go to virial radius and beyond, we see that there are cold clumps, there are colder components, and the dynamics in the gas is really impressive. So we have really a spread of motions. So can we actually recover all this complexity? Well, the first thing we need to do, we need to see what will actually happen in projection, and this bottom figure shows exactly the same plot. It's just the last slide. It's just that we're using projected radius instead of three-dimensional. And interestingly, we see that all these clumps that are present outside of the virial radius in projection actually will be visible within the virial radius, right? So if you have spectra and we can do multi-temperature component fit, we can actually look at dynamics of a cold gas, and it will tell us what is happening in virializing regions, which I don't think we really appreciate before. So this whole exercise, its crosses show basically what we can recover with our observational approaches, and the white curves show that we will comfortably recover as the dominant hot component in this type of systems, and then the green and yellow crosses show how well we can in principle probe additional components, all right? So I think overall the consistency is pretty good, given that it's an extremely complex spectra, and I don't think our tools are, in advanced enough level to handle all this complexity. But overall, we can pretty good sample the ICM even in the outskirts. Skipping some additional figures and structure functions that we can do. If there are questions, happy to answer. And I'm just leaving my takeaway summary points. Thank you.
Great. Okay. Raj, start us off. Yeah, people line up for questions.
I have a question regarding the recent paper with Annie that we showed of all the different clusters and the power spectrum. Yes, yeah, this one. So I'm wondering if the structure function of density looks quite, and then I'm wondering if that is due to if you have many different driving fields across different clusters, and if you try to, I don't know how you plot the mean there, but if you have many different driving fields that may flatten out all the different clusters.
I mean, we cannot really decompose different driving scales. We are basically measuring everything that is driven by whatever physics you can imagine. Of course, there could be additional driving scales, and sure, I mean, we can come up with all the different exotic solutions. I would say within the current error bars, we're still consistent with any physically motivated model, so I think it's a bit overstretched. But if we have to have more data and we can reduce this uncertainty, probably this type of questions we can start studying. In general, the scales we are looking are varying from 500 to like 50, 80 kiloparsecs. So you can imagine that a lot could happen on these scales. Yeah. Yeah.
Like driving the velocity spectrum, I wonder if you use a series compatible or compatible turbulence, and what is the output energy and then affect the result?
So the analytical here we just assume that it's very subsonic and no compressibility effects in analytical arguments. which could be a bit oversimplification, right? But these are just analytical arguments. But simulations, if there are any compressibility effects, should show that. That's why we're calibrating things with simulations, and I think it's partially responsible for the observed scatter in our relation. Yes. Hi.
So, two questions. One is on this relation. So you have Mach numbers there. I think I couldn't read it from the back. So one Mach numbers. That was this Mach 1.
Yeah. So this is basically we are measuring one component along the line of sight. You can, if you assume that motions are isotropic, you just multiply by factor 1.7.
So the actual Mach numbers
are higher. Three-dimensional Mach numbers will be slightly higher. Upper limits in merging systems could be 1. Yes, in this case. Yeah.
The other quick question is the resonance number that you get from your nature. So normally you would say it's only 100 or so. But if your new result, you would say it's at least 1,000 or 10,000. Is that the conclusion?
So we got the limit, right? So we basically can say it is maybe at least few hundred, but we cannot have the upper limit, right? Because it's just a constraint. Comes from.
Can we go back to comparison of the density with simulations, right? So this plot. Are you concerned that it looks like slope is off?
Again, within the uncertainties, it's very hard to say. This is just one sigma uncertainty over here, right? Maybe we basically did everything we could to investigate if there are any observational biases on this side. And frankly, all corrections are basically working in recovering some power. And I mean, we could actually, sometimes produce even higher end, but not the lower one. So we couldn't find any disagreements. Of course, this is just one type of simulation. So ideally, we want to make these predictions with more modern, more updated simulations with more included physics. Probably it will resolve the problem. Yeah.
Oh, Irina, great talk. Thanks. I have a comment and then a question. The comment is that we performed small-scale dynamo simulations of clusters under the collisionless approximation, and we were able to do by self-consistently calculating the evolution from the simulations, directly from the simulations, the evolution of the viscosity. We got a final viscosity that is 2 orders of magnitude than the expected one from the collisional, and it fits quite well your comma results. So this is a comment. And the question regards the same diagram that you showed to Dimitri. Yes, perhaps the upper left diagram could be a signal that we have to take into account collisionless effects in these simulations at those scales, right?
That's one of the missing physics
collisionless
right now.
MAGD.
Yeah, that could be, yeah. And these simulations do not have magnetic fields, so also magnetic fields.
Yeah, of course, but maybe this.
So, yeah.
Do you agree with this?
I agree with that. This could be one of the sources. I mean, the obvious solution also will be here to kind of modify maybe our physics of agent feedback that could also have some effect. But yeah.
Okay.
Ideally, we want to have like simulations that consistently include all pieces of physics step by step, and then we can just see which ones are bringing us, better consistency with observations. Yeah.
Okay.
Thank you.
Thanks.
One quick question. Will you have the next speaker come up?
So just a quick, more of a comment than a question, and really just sort of setting on the stage for later discussion. Irina, I think these are great results. It sort of underlines the idea that, there are a number of people here from the space physics community that study turbulence collisionlessly with kinetic models. And, generally in those models, viscosity and resistivity are terrible approximations to what the dissipation is. Question whether things like the Reynolds number, which really cannot be defined in a collisionless plasma because there is no viscosity. Viscosity is derived in the limit of small mean free path. And when you're in the limit, where you're in the opposite limit, it just is inapplicable. Everything is anisotropic, depends on the magnetic field. And I think that Irina's results really highlight that fact. So I think that hopefully this is something we can discuss a lot about. How do you connect these large-scale fluid simulations that have been done in this community for decades to the smaller-scale kinetic physics of what the real microphysical dissipation is and the properties of that and how it leads to dissipation of the turbulent energy.
Great point. All right, let's thank Irina one more time.